Hi again. Welcome back to ENAE 788M, Hands-on Autonomous Aerial Robotics. In the last project, Project 1A, you implemented the orientation estimator using a magic filter. But we also said that you can definitely have a better estimates if you use a Bayesian based filter such as the Bayes filter or the Kalman filter or any of its variants. Today's class, we will dive right into talking about the Bayes and the Kalman filter. In the next class, we will talk about the extensions of Kalman filters. So let's dive right into it. So the first question is, why filter? So let's go through a story first, and then we take a ride and then think about why we need to filter, right? It's the apocalyptic year 2050 and GPS is down. The only way to localize yourself is to detect the giant April tag marking on the ground. Now, imagine that you have a quadrotor flying over this apocalyptic April tag city, right, as shown here. Now, the quadrotor is flying, it's following some trajectory, and the trajectory is shown as follows, right? This quadrotor is not any ordinary quadrotor. It belongs to the police and who are patrolling the area for alien intruders. Remember, it's 2050 and it's an apocalyptic time and we are under attack by alien intruders, right? This quadrotor is required to follow some trajectory for which it needs an estimate of its position, right? To follow something, it has to know how it's moving. So, okay, I've just shown a random coordinate axis here, which we will call the word frame, right? So now the quadrotor is at state x0, where it knows its location, right? The state xt here is defined as the 3D position x, y, and z of the center of mass of the quadrotor in the world frame, right? And the thing the camera sees is shown in the red pyramid here. So now the quadrotor moves a little bit to x1. It was at x0, it moved a little bit, now it's at x1. Here, the quote unquote state xt is a time varying quantity and denotes the 3D position of the quadrotor body center in the world frame, like we said before, right? That includes x, y, and z of the body center in the world frame. We see that the parts of the ground the bottom camera sees at x0 and x1 are different, right? A simple fact about the April tag is that you need to see the complete April tag to be able to localize yourself. If you just see just a part of the tag, you don't really know what that tag is, right? Because each April tag is of a particular marking. They have some commonalities among the different markings, but the key difference is that each of the tags have a separate unique identification number. Think of this as like a number plate for your car, but in a visual sense, right? It doesn't have any numbers. The data is encoded in the way these black and white squares are arranged, right? Cool. They always will have a white border, so just to get an idea. But now, oops, we don't see the complete April tag at x1, right? How do you localize yourself? So one simple way is to predict where you are by assuming a simple motion model, such as a constant velocity or acceleration, or you can think of even more fancier ways wherein you compute the accelerations from the motor speeds, right? So that's the second step. Now, we move again. We are now at x2. We see a complete April tag again. Awesome. So we can localize ourselves again. The story we just experienced together is how a general robotic system functions. That is, if the robot first moves, then it predicts its own state and finally senses its surrounding and updates its state, right? So the big catch here is that the update has to take into account the uncertainties of the prediction and sensing. So whenever we predict, we are not going to be perfect, so there is a certain uncertainty associated with it. Whenever we sense something, the sensors are not perfect. Like even with like an expensive $100,000 LiDAR, there is a little bit of noise, right? So we want to model that as well. So again, we move, we predict, we sense, and then we update for accounting for all the uncertainties and so on, right? So essentially what we want to do is correct our belief by taking into account the observation, like we said before. And we want to do all this while accounting for the uncertainty in prediction and sensing. A simple way to do that is by using a Bayes filter, right? Like we said before, we want to predict the current state xt given the previous state xt minus 1, the current input ut, and the current observation zt, right? So the state here, the previous state here is shown as follows, and then we want to predict the current state xt given ut, and we are observing zt, right? So essentially what this entails in the probability or the Bayesian sense is that we want to find out or maximize the probability of the state xt given all my observations till the current observation and all my previous states and all my previous inputs, right? So yeah, so here for the particular example we just talked about in the apocalyptic city, our state vector is the position of the body center in the word frame. ZT observation is we are obtaining the location with respect to an April tag. So we are assuming that we know the locations of these April tags in some arbitrary word frame. So we are getting that. And UT is a motion model which we just talked about, is being estimated, computed from the motor speeds. That is, the quadrotor has 4 motors and each of them have a different speed because the quadrotor is moving in some orientation. So we have omega 1, 2, 3, and 4, right? Cool. Now, the question is, how should my belief of X change in order to take into account the current observation Z? So, for example, if I think that I am at 0, 0, 0, but my observation says that I'm at 1, 0, 0, how should these two be blended together, right? It's not as simple as you saying that, okay, just going to take my observation, put it on my X, and be done with it. That is not as simple because you're not modeling the uncertainties here, right? The answer is very simple. Bayes theorem, right? What Bayes theorem says is you have p z given x and p of x. You can estimate p of x given z comma u by this Bayesian formula, right? So here p z given x is called the likelihood function. P of x is called the prior on my state, which comes from various sources, and p of x given z comma u, which is the probability of the state given my observation and the amount of input, is called the posterior distribution. So, like to recap, the simple Bayesian graph looks like this. Like you are, like all the things in red are the states, and you have previous state feeding into the current state, and for each current state you have your current input, and you're seeing some observation. And at every time step, you are trying to maximize your belief by taking into account the observation and what you thought you were, where you were, right? So that's P of x t given z and u, right? So the prior here is defined by P of x naught, which is at time t equal to 0. So you believe that you have a prior of where you were. So for example, it could be at 0, 0, 0. And you have a process model, which is given by this function f, which is saying given my previous state and my current input, how was my state, the next state going to look like, right? So this could be as simple as assuming a constant velocity model for our case, and given the motor speeds, you have an acceleration. So you can do simple Newtonian physics, right? So then you have the measurement model, which is this function g, that is g of zt given xt, that is what is the probability of my observation given my current state, and how do I look at it? So the prediction step is fairly simple. You just do the marginalization on all the previous states, and then the update step is the same as what we talked about before, right? You just apply the Bayes rule, and this is the Bayesian filter. But this is pretty complicated because for the Bayes filter, you need to make a history of all the states, right? And at every point in time, you have to do an infinite sum up to the first state. And if it's like you're talking about in continuous domain, you're integrating it every time. If you're talking about discrete time, so if you are at like time 100 second and you had one sample every second, you have to sum up 100 samples, which can get pretty exhaustive if you have a lot of sensors and your sensor rate is pretty high, right? So you don't want to do this. So to simplify life, we are going to make some assumptions. So the first one is called the Markov property, which just says that the next state, given all the previous states, is exactly equivalent to the next state given the current state, right? The future, that is, the future state of the system is conditionally independent of the past states given the current state. So that's mathematically as a base graph is shown here, and these two are equivalent, right? So you literally basically just chopped off a bunch of nodes in the back, and you just say, okay, this is exactly the same as collapsing everything from 0 to xt minus 1 to xt minus 1. That's what's shown here. So next we make a simpler, even more simpler assumption. We say, okay, the prior is given by a Gaussian distribution, and let's say the state is some n by 1 vector, and the mean is going to be the exact same n by 1 vector, and the covariance is an n by n matrix, right? In this case, I'm showing a Gaussian wherein it's a n value is 2, and the z-axis is just showing you the amplitude, right? The thing in the center is the mean, and the 1 sigma covariance is representing the covariance matrix, sigma naught here, right? So for people who have forgotten what a Gaussian looks like, there is the equation here, right? And so then you also make some more assumptions. You say, okay, my process model is linear with additive white Gaussian noise, and that looks like this. You have current state is equal to some linear function at into previous state plus some linear function bt into my current input plus noise. And again, the noise looks like a Gaussian, and where qt is some matrix which characterizes this noise, right? And these are some more concrete details of the sizes of these things, right? And we also assume that the measurement model G is linear with additive white Gaussian noise again. So Z is going to look like some observation matrix C into my state vector plus some noise, and like before, the noise is again Gaussian, right? And RT is some matrix which characterizes this noise. So remember here that QT is the process model noise. It's basically describing how much noise there is in my predictions, and RT is basically characterizing how noisy my sensors are. So if you have an expensive sensor, the value of RT could be small, and if you have a really good nonlinear, nice, pretty model, and you know that all your stuff is linear, then the value of QT could be small, right? So, and again, like here are more concrete details about the sizes of Z, V, C, and R, right? So hence, the state xt is represented by a Gaussian distribution, right? So again, xt is denoted by this normal distribution with the mean at mu t and covariance of sigma t, which we want to update on the fly, right? So this happens because a linear or an affine operation on the Gaussian distribution gives us a Gaussian distribution. I'll leave this as an exercise for people to work out for why it is so, right? Cool. So now let's move on to the Kalman filter prediction step. The prediction step is also called as the motion model or transition model or process update. Let's modify the previous base filter process model using the Markovian property, and it would look something like this, right? And the prediction is fairly simple. So we call the thing with the bar is for prediction, denoting the prediction. So we have the mean predicted is just the linear combination of the previous mu plus b a linear and the scaled linear combination of the current input, right? And covariance looks like that, right? So if you don't really understand why this is so, you can just work out these equations on your own, right? So if I start plotting the 1D slice of that 2D example we took before, the prior could look something like this, and my prediction looks like this, right? Observe one thing, that the prediction covariance has increased because the spread of the prediction has increased, or the covariance has increased because we are not perfect in our prediction, right? So this is always going to happen. So if you do not really, you only keep predicting, this will basically die down, and at infinite time this is just going to become a uniform distribution, right? So let's move on now. But we already have a sensor, so we want to get an update. So the update step is also called the measurement model or the update. So let's modify the base filter measurement update, which was using the base rule before, and we apply all the stuff we talked about and we assumed about the linearity here, right? So this will give us a jointly normal distribution, so with the mean and covariance states as shown. So we want to fuse these guys into one distribution. So let's recall some properties about conditional distributions first before we do that. right? So recall that if X is a multivariate Gaussian distribution with the mean mu as mu1 and mu2, where X is x1 and x2, and covariance is given as follows. The conditional density function f x1 given x2, wherein you observe some small x1 conditioned upon small x2, is a multivariate Gaussian distribution with the mean and covariance as shown here. So for people who this does not sound very familiar, you can read up some books on probability, and I will leave that as an exercise for you to work out. So remember that here the covariance matrix of x1 conditioned upon x2 is the shear complement of sigma to 2, right? Cool. So next, let's move on. Now we want to estimate the normal distribution, that is mean and covariance of the distribution xt conditioned upon zt, like we talked about before, right? So that will look something like this. For people wondering how this came in, it just comes from the previous step and we just plugged everything in, right? So now let's define this little thing like sigma bar thing as kt to be the Kalman gain. The derivation for this is pretty long, and you can read the original Kalman paper if you are curious as to how that comes in, but you can just take my word for it that this is correct, right? And my updated mu t and sigma t will look like this. Remember that this has taken both the prediction, which is in the golden color here, and it has also taken all my observations, which is in blue color here, right? So remember from the previous slide, our prediction looked like that. Now we see a measurement which looks like this, and we fuse both of these guys and we get a posterior. The posterior is my final update of what my belief is, where my state should look like, right? Observe that both the prediction and measurement have wider covariances than the posterior, because that's the whole idea here. You want to reduce your covariance or bound it when you're getting a prediction and a measurement and they have some correlation with respect to each other, right? So now let's dive into some intuitive understanding of how the Kalman gain works, right? I'm going to put the equation of the Kalman gain back again. This Kalman gain is basically a weight factor which weighs the trust between the measurement and the prediction, right? So if you have a perfect sensor, like we discussed before, your RT value will be 0, right? So you're basically going to have equations which look like this, right? So your perfect sensor basically is saying that I'm not going to trust my motion model at all. I'm just going to take my measurements directly, put it in my state, which is sort of obvious, right? So if you have like $1 million LiDAR, why would you not just use the state estimates from that? Instead, why would you have like a little assumption about everything being linear and just directly have an equation? That doesn't make sense, right? But you can, on the other hand, you can have a horrendous sensor wherein the sensor has gone corrupt, or it's horribly built and there is some error, or it's like super cheap so it does not work well, right? So wherein RT tends to infinity here. And in this case, it will only trust my motion model, right? Because it's saying, okay, my sensor is so bad that I'm going to just assume what my designer said in the motion model is correct. So then this is just a recap of what we have in the Kalman filter. So we have a prior, we have a process model, and we have a measurement model. So feel free to understand how this works. The implementation of a Kalman filter is fairly trivial. So, and I would leave this as a exercise for you to try out on the IMU data you already have for the project 1A, right? So let's go about some facts about the Kalman filter. So if the distribution is not Gaussian, like we assume, right? The Kalman filter is a minimum variance linear estimator. However, in this case, the noise must be uncorrelated with the initial state x0. If it's correlated with the initial state x0, the minimum variance thing will not hold, because the outputs will start diverging randomly depending on the nonlinear function, right? The variance again never increases due to receiving a measurement. Of course, this is a heavy sentence, but it's based on the fact that my sensor is not absolute garbage, right? It's not like R is not tending to infinity, it's some sensible value, right? And the variance update is independent of the measurement realization. What it's saying is the variance equations which we saw before does not rely on what the exact measurement value was, right? Which is kind of obvious. It only depends upon the values of R which and the difference to what it thinks the differences are, right? Cool. So a fun fact is that a linear Kalman filter was used in the Apollo 11 to estimate the orientation. So it's pretty cool that your whatever was 1960s space technology is being used on racing quadrotors today. So again, let's revisit the attitude estimation on the IMU problem as before. So you have an IMU which is rotating in space, and you assume that you have a 6 degree of freedom IMU, which gives us angular velocities. This part is called the gyroscope, and we have linear accelerations. This part is called the accelerometer, right? So we want to estimate the orientation in world frame. Orientation is also called attitude. Orientation here is parameterized as ZYX Euler angles, right? So okay, we want to estimate the state X, which is ZYX Euler angles. We have the measurements A and omega. We here assume that the bias has been removed and the change in bias is negligible, right? So the prior here is that we know the initial state, something, from either a motion capture system or we just started at rest, right? The motion model is just saying that, okay, my IMU state, my omegas being integrated will give me the estimate of my next state, right? So this is all based on the gyro values. And my measurement model is completely based on the accelerometer. So my accelerometer gives me angles. Remember that yaw cannot be determined uniquely with this parameterization. I just put the equation here just for the sake of completeness, right? So again, motion model comes from the gyroscope, measurement model comes from the accelerometer. It's analogous to our complementary filter, wherein we had both gyro and accelerometer and we were low passing and high passing them and fusing them. In this case, we fuse them in a motion model and a measurement model. The reason why we do the motion model for the gyroscope is because motion model generally runs much faster and more frequently than the measurement model, right? So in a real system, the measurement model could come something like a camera, wherein it would only run at 30 hertz, but the motion model can run at 100 hertz. So your effective filter rate runs at 100 hertz. So that's the idea here. So you have a gyroscope as the motion model, which is good for higher or faster speed stuff, higher frequency stuff. Measurement model is given by the accelerometer, which is good for low frequency stuff, right? So the next question is why or why not a Kalman filter? Some of the advantages of using a Kalman filter are as follows. It's super simple, right? The matrix operations are very, very efficient, and this can be easily implemented on embedded platforms. The disadvantages is that it assumes everything is linear and Gaussian, which is seldom true in reality. Can only deal with unimodal distributions. So this is pretty bad if you want to do flips and things like that. So in the next lecture, we will talk about how we can modify this Kalman filter to make it handle nonlinearities better. See you in the next class. Bye.